Hey, this scribblecast is looking at pH. We've already looked at acids, some definitions of acids. In the solution section, we also talked about concentrations. When we look at acids and concentration, and since we deal with those so often, we or I guess chemists have come up with a way of quantifying or not categorizing, but looking at strengths of acids. And the tool they use is something called a pH. You've probably heard that term in lots of other places, like the pH of a pool. You need to keep it at a certain pH in order for the chlorine to work. And there's lots of places where you might have heard of pH before. Basically, pH is it's a scale. It's actually a logarithmic scale. Don't worry about that word. But it's a scale that instead of looking at concentrations, we just sort of apply it to numbers. So instead of saying the concentration of something is 0.01 molar, we say that thing has a pH of, say, 2, or it has a pH of 4. And those certain pH numbers mean something. Okay, and we can relate those from one to the other. Here's a nice little scale that I found on the internet. I actually got copyright for it, but I think it's public domain. Anyway, it's a nice little scale that indicates pH on one side and pOH on the other side. We'll look in the next scribblecast at pOH. But just take a look at the pH of some common substances. So like here, bleach has a pH of 13, whereas something like gastric acid, or the acid in your stomach, has a pH of 1. And so if something's very acidic, it seems like it has a lower number, closer to 0. And if something is not very acidic at all, it would have a pH of a higher number. Actually, right in the middle, as we're looking at the scale, it seems like all the stuff on the bottom here is fairly acidic. So if you have a pH of something less than 7, it's acidic. If you have a pH of more than 7, up to 14, it's basic. So, something like orange juice has a pH of 3. That's interesting, eh? Orange juice, you wouldn't think it's very acidic, but it has a pH of 3, indicating that maybe it's not a strong acid, but certainly it's an acid. I remember one time when I was eating a lot of raw pineapple, and you can try this as an experiment. Take some pineapple and eat, I don't know, 4 or 5 of them, and eat it consistently every day. And you'll notice that it'll wear the enamel down on your teeth. And it sort of wears it down, I don't know, to the nerve, but it wears it down enough so that hot and cold things drive you crazy. You may or may not want to participate in that experiment. Okay, so the pH of a solution refers to its acidity. A pH as close to 0 as you can gets to be a very strong acid. As the pH decreases to 7, 7 would be something that's very neutral, like distilled water. And as you go higher than 7, you get to a pH of something like 14, which would be not acidic at all, and actually it would be the opposite. It would be very, very basic. Okay, so pH is a logarithmic scale. Now, you may want to look up on the internet or somewhere else and just look up things like battery acid or milk or any of these other kind of substances. Look them up online, see what their pH is, and see how they relate to some of these other ones that we've given here. Okay, so one thing that we need to do is we need to be able to convert between a concentration, because we've done concentrations before, right? 0.01 molar, for example. We need to be able to convert between a concentration like this and a pH. So there's a handy-dandy formula that helps us do that. So we can indicate the concentration of something in terms of its hydronium ions. So we can say the concentration of hydronium ions is something. but then it's often nicer to be able to express that as a pH. So here's our formula that we can use to convert between hydronium ions and pH. So for example, here's one. The concentration of hydronium ions is 0.5 moles per liter. What is the pH? So all I would do is plug numbers into my calculator or into my formula. 0.500 moles per liter. So on my handy dandy calculator, which hopefully it will work here quickly for me, I go negative, where's my negative button? Negative log of 0.5. Go. So my answer came out to be, in this case here, the pH would be 0.3. Sig fig 0.3 0 0. I'm just worried about sig figs here at the end. Yeah, that would be correct there. So 3 sig figs here, and after the decimal place, I have 3 sig figs there. Okay, so just using that formula. Let's try a couple more. Calculate the pH of a solution which contains 0.022 moles per liter of hydronium ions. So pH equals negative log of 0.022 moles per liter. Okay, so negative log of 0.022. Go. So in this case, my answer came out to 1.657577, etc. Now, in sig figs with pHs, it's a little bit different than you've seen in sig figs in previous classes. The sig figs that you're given originally, like in this question here, leading zeros don't count. So in this case here, I'd only have 2 sig figs. In any pH measurement, the significant figures, or the number out front, it's sort of like a leading zero. The number out front doesn't count for sig figs. So if I have 2 sig figs originally, in this part here after the decimal place, I need to give 2 digits. So my pH will be, rounded to the proper number of sig figs, would be 1.66. Notice I have 2 decimal places. So 2 decimal places relate to the 2 sig figs that were in the original question. Okay, so 1.66, fairly acidic. You know, getting down in the zeros, the ones, the twos range, something's fairly acidic. Okay, so we have figured out how to go from hydronium ions to pH. Now we should be able to take something that has a pH and determine the number of hydronium ions, or the concentration of hydronium ions. Notice if I do that, I would plug my pH in here, but I've got this little function, a logarithmic function, that's sort of difficult to deal with if I'm trying to manipulate the formula. So it's probably just best to memorize this formula. So if I wanted to solve for hydronium ions, what I do is on my calculator I go 10 to the negative pH. Often on your calculator you'll see a button like this, y to the x. That's the one that you want to use. Okay, so if I know the pH, I'm going to use this formula. Hydronium ions are equal to 10 to the negative pH. Okay, so in this particular case, my pH is 4.5, so it'll be 10 to the negative 4.5. Let me try that on my calculator. Clear. Okay, 10 to the, where's my to the button on this calculator? Uh-oh. This calculator doesn't have a to the button. Oh, there it is. Sorry. Okay, 10 to the negative 4.5. Go. Okay, so the answer to this was 3. Now, in this question here, the numbers after the decimal place is 1, so I can only give 1 sig fig. So my hydronium ion is just going to be 3 times 10 to the minus 5. I've got scientific notation there. But here, my sig figs, I can only give 1 sig fig because in my pH, I only had 1 decimal place. Now, try that thing on your calculator and make sure your calculator is going okay there for you. Here's some maybe to try it on. So, find the hydronium ion concentration if your pH is 12.2 or if it's 7.00. Notice 1 sig fig here, 2 sig figs here, 2 sig figs there. So you may want to pause your recording, try and figure out your hydronium ion concentrations from those. Okay, pause. Okay, now that you're back playing, here are the answers that I came up with. So just see if your numbers correspond to the numbers that I got there. Okay, hopefully they do. If you're having trouble with that calculation on your calculator, get a hold of your instructor, talk to a friend. Make sure that you can do that change, that calculation before you go on. Here's another one. I forgot to show you this slide, but here's an example of using this formula here to find the pH if you're given hydronium ions. You may want to pause again, try and use this formula here to figure out the pH of those. Okay, I assume that you have paused and now press play again. There's the answers that I got. So you can just sort of see if you are on the right track. If you're not, again, grab some help from somebody. Now, one thing, just as a good segue into looking at pOH, the one relationship that you'll find that's actually quite interesting and quite good is that the sum of the pH of a solution and the pOH of a solution always has to come out to 14. So that means you'll never have a pH of 15 or a pOH of, you know, a number outside of that. They always have to add up to 14. It's a nice relationship because often you're given the pH of a solution and maybe you need to know what the pOH is. So all you have to do is make sure that you get a number for a pOH that when you add this to it, you come up with 14. I'll just show it to you with the formula. pH plus pOH is equal to 14. So if my pH is 1.3, now I'm going to subtract the pOH is equal to 14 minus 1.3. So the pOH of that solution would be 12.7. Notice I retain the same number of decimal places. Okay, so that's a nice relationship between pH and pOH. And we'll look in the next Scribblecast at similar calculations that we can do with pOH. So, in the Scribblecast, we've looked specifically at pH, and pH is a quantity or a measurement that's used to describe or relate, compare acidity of solutions. So if you have a pH close down to 0 or close down to 1, that means it's very acidic. If you have a pH that's close to 7, that's like it's neutral. And if you have a pH of something that's close to 14, that's very non-acidic. In fact, that's something that's very basic. Okay, so pH is a logarithmic scale, helps us just look at numbers and compare them to others. Okay,